Welcome back. In this video, we're going to talk about how regular expressions are used to construct a full lexical specification of a programming language. Before we get started, I want to quickly summarize notation for regular expressions. One of the shorthands we talked about last time is A+, which means a sequence of at least one A, or the language A star. Sometimes you'll see a vertical bar used instead of union, so A plus B can also be written A vertical bar B. An optional A is an abbreviation for the regular expression A plus epsilon. And then we had character ranges, which allows us to do a big union of a bunch of characters in order. And then one more that's used that's actually fairly important, but we didn't discuss last time, is the complement of a character range. So this expression here means any character except the characters A through Z. So in the last lecture, we talked about a specification for the following predicate. Given a string S, is it in the language, that's the function L, of a regular expression? That is, we defined a language of regular expressions, and we talked about their semantics in terms of sets of strings. And so for any given regular expression, we could reason out by hand whether a given string was in that language or not. And this turns out not to be enough for what we want to do. So just to review, what is it we want to do? Well, we're given an input, which is a bunch of characters. So here's a string of characters. And it can be much longer than just 7 characters. And what we actually want to do is to partition this string. We want to drop lines in this string to divide it up into the words of the language. Now, of course, each one of these words ought to be in the language of some regular expression. But just having a definition of a yes-no answer is not quite the same thing as having a method for partitioning a string into its constituent parts. And so we're going to have to adapt regular expressions to this problem. And that will require some small extensions, and that's what this video is all about. So let's talk about how to do this. The first thing we're going to do when we want to design the lexical specification of a language is we have to write a regular expression for the lexemes of each of the token classes. And we talked about how to do this last time. So for the numbers, we might use digit plus as our regular expression, and we might have a category of keywords, which is just a list of all the keywords in the language. We will have some category perhaps of identifiers. There's the definition we talked about last time, sequences of letters or digits that begin with a letter. And then we'll have a bunch of punctuation, things like open parens, close parens, etc. So we write down a whole set of regular expressions, one for each syntactic category in the language. And that's the starting point for our lexical specification. Now, as the second step, what we're going to do is we're going to construct a gigantic regular expression which just matches all the lexemes for all the tokens. And this is just the union of all the regular expressions that we wrote down on the previous slide. So we just take the union of all those regular expressions, and that forms the lexical specification of the language. And we'll just write this out. We don't really care what these regular expressions are, but they're just some set R1, R2, and so on, and the whole thing we're going to call R. And now here's the heart of how we actually use this lexical specification to perform lexical analysis. So let's consider an input. The input's a string x1 up to xn. And now for every prefix of that input, okay, we're going to check whether it's in the language of the regular expression. So we're going to look at some prefix starting with the first character, and we're going to ask ourselves, is it in the language of that big regular expression? And if it is in the language, well, then we know, in particular, that that prefix is in the language of one of the constituent regular expressions, because remember that R is equal to the sum of all the different token classes of our language. Okay, so we know that this prefix x1 through xi is in the language of some rj. Okay, and so that we know that that's a word in our language. It's it's in one of the token classes that we're interested in. And so what we do is we simply delete that prefix from the input, and then we go back to 3, and we repeat. And in this way, we keep biting off prefixes of the input, and we'll do this until the string is empty, and then we have lexically analyzed the entire program. Now, this algorithm has a couple of ambiguities. There are a couple of things that are underspecified, and those are actually interesting. And so let's take a moment and talk about those. The first question is, how much input is actually used? So let's consider the following situation. Let's say that we have that x1 through xi is in the language of our lexical specification. And let's say there's a different prefix that's also in the language of our lexical specification. And of course here I is not equal to j. Now what does that look like? Well, it would look like the following kind of situation. We would have our input string, and we have two different prefixes of the input that are both valid token classes. And the question is, which one of these do we want? And just to be concrete here, to give a concrete example, let's consider what happens when a double equals is at the beginning of the input. So after we've chopped off a bunch of other input, perhaps we have this substring or this prefix of the input that we're looking at, and the question is, should this be regarded as a single equals, which would be an assignment operator in most languages, or would it be regarded as a double equals, which in some languages is a comparison operator? And this is an example we've looked at before and discussed, and there's actually a well-defined answer to this question, and it is that we should always take the longer one, and this has a name. It's called the maximal munch. So the rule is that when faced with a choice of two different prefixes of the input, either of which would be a valid token, we should always choose the longer one. And the reason for this is that's just the way humans themselves read things. So when we see a double equals, we don't see two different equal operators, we see a double equals. And if I look at at this sentence that I wrote up here, when we look at HOW, we don't see three letters. We gather that all together in one long token. We go as far as we can until we see a separator. And so because this is the way humans work, we make the tools work the same way. And this normally, or almost always, does the right thing. A second question is, which token should be used if more than one token matches? So what do I mean by that? Well, again, we have our prefix of the input, and it's in the language of our lexical specification. And just remember that the lexical specification itself, again, is made up as the union of a bunch of regular expressions for token classes. Now, since this prefix is in the language of the lexical specification, that means that it must be in the language of some particular token class, RJ. But nothing says that it isn't also in the language of a completely different token class, meaning that this same string could be interpreted as one of two different tokens. And the question is, if this happens, which one should we pick? So, for example, just to make this concrete, recall that we could have a lexical specification for keywords, which would be things like if, and else, and so on, and also for identifiers. And an identifier was a letter followed by a letter or a digit repeated. Okay. And if you look at these two specifications, you'll see that the string if is both of them. So if is in the language of keywords, and it's also in the language of the identifiers. And so should we treat if as a keyword or an identifier? Now, the normal rule in most languages is that if it's a keyword, then it's always a keyword, and the identifiers actually don't include the keywords. But actually, it's a real pain to write out the identifiers in such a way that you explicitly exclude the keywords. This is a much more natural definition that I've written here for the identifiers. And so the way this gets resolved is by a priority ordering. And typically, the rule is to choose the one listed first. Okay? So when there is a choice, when there is more than one token class to which a string might belong, the one that is listed first is given higher priority. So in our file defining our lexical specification, we would put the keywords before the identifiers, just as we have done here. The final question is what to do if no rule matches. What if I have a prefix of the input that is not in the language of my lexical specification? Now, this can actually arise. Certainly, there are lots and lots of strings that are not going to be in the language of the lexical specification of most languages. And the question is how to handle that situation. So it's very important for compilers to do good error handling. They can't simply crash. You need to be able to give the user, the programmer, feedback about where the error is and what kind of error it is. So we do need to handle this gracefully. And the best solution for lexical analysis is to not do this. So don't let this ever happen. Okay, so what we want to do instead is to write a category of error strings. So all the strings not in the lexical specification of the language. So we write out a regular expression. Again, this is another regular expression here for all the possible error strings, all the possible erroneous strings that could occur as invalid lexical input. And then we put it last. Put it last in priority so that it will match after everything else matches. And the reason for putting it last is that this actually allows us to be a little bit sloppy in how we define the error strings. It can actually overlap with earlier regular expressions. We can include things in the error strings that are in fact not errors. But if we put it last in priority, then it will only match if no earlier regular expression matched. And so in fact it will only catch the error strings. And then the action that we'll take when we match the error string will be to print an error message and give the nice feedback like where it is in the file and such. To wrap up this video, regular expressions are a very nice and concise notation for string patterns, but to use them in lexical analysis requires a couple of small extensions. So in particular, there's a couple of ambiguities we have to resolve. We want our matches to be as long as possible. So we take as much input at a time as we can, and we also want to choose the highest priority match. So the regular expressions are given a priority, the different token classes have priorities, and when there's a tie, when the same prefix of the input could match more than one, we pick the one that has the highest priority. And typically this is done just by listing them in order in a file, and the ones listed first have higher priority over the ones listed later. I just want to warn you that when you go to write lexical specifications, when you go to actually implement Lexar for a language, the interaction of these two rules, that we take the longest possible matches and we break ties in favor of the highest priority rules, that these lead to some tricky situations, and it's not always obvious that you're getting exactly what you want. You have to think carefully about the ordering of the rules and exactly how you write the rules so that you get the behavior that you desire. And finally, to handle errors, we typically write out a catch-all regular expression that soaks up all the possible erroneous strings and give it the lowest priority so that it only triggers if no valid token class matches some piece of the input. And finally, we haven't discussed these yet, but there are very good algorithms known for implementing all of this. And in fact, we'll be able to do it in only a single pass over the input and with very few operations per character, with just a simple table lookup. And this will be the subject of our future videos. Welcome back. In this video, we're going to talk about finite automata, which we'll see in future videos are a good implementation model for regular expressions. So in the last few videos, we've been talking about regular expressions, which we use as the specification language for lexical analysis. And in this video, we're going to start something new. We're going to talk about finite automata, which are the are very convenient as an implementation mechanism for regular expressions. And so regular expressions and finite automata are very closely related. It turns out that they can specify exactly the same languages called the regular languages. We won't prove that in this course, but we'll certainly make use of that fact. So moving right along, what is a finite automaton? Well, here's a typical definition as you might see it in a automata theory textbook. Finite automaton consists of an input alphabet, so these are the set of characters that it can read. It has a finite set of states, should probably emphasize that. This is what makes it a finite automaton, is that it has some set of states that it can be in. One of those states is special and is designated as the start state. Some subset of the states are accepting states. So these are the states that, well, we'll define them more in a minute, but intuitively, if the automaton terminates after reading some input in one of these states, then it accepts the input, otherwise it rejects the input. And finally, the automaton has some set of state transitions. That is, if it's in one state, it can read some input and go to another state. So let's look at that in a little more detail. So a transition in a finite automaton, if I'm in this case, I've written out one particular transition. Here, if we're in state 1 and we read the input A, then the automaton can move to state 2. Okay, and there could be lots of different transitions for the automaton from different states and different inputs. And it's read in the following way. If we're in state 1 on input A, we will go to state 2. And if the automaton ends in an accepting state, when it gets to the end of the input, then it's going to do what's called accepting the string, meaning that it will say, yes, that string was in the language of this machine. So intuitively, the automaton starts in the start state, and it repeatedly reads inputs, one input character at a time, makes a transition. So it'll see what kind of transition it can make out of its current state based on that input to another state. And if when it's done reading the input, it's in one of the final states, then it will accept. Otherwise, it's going to reject the input. Now, what are the situations in which it rejects? Well, if it terminates in a state S, that's not one of the final or accepting states. Okay, so if it ends in any other state besides one of the accepting states, then it's going to reject. If the machine gets stuck, meaning it finds itself in a state and there's no transition out of that state on the input. So in particular, let's say that it's in some state S and the input is A and there's no transition. There's no transition specified for state S on input A, so the machine can't move anywhere and it gets stuck, and that's also a rejecting state. And so in these two situations, if either it gets to the end of the input and is not in a final state, or if it never reaches the end of the input because it gets stuck, in both of those cases, it rejects the string. That string is not in the language of the finite automaton. Now, there's an alternative notation for finite automata that I think is more intuitive for examples. And so we're going to emphasize that way of writing them out. In this notation, a state is represented as a node in a graph, which we just draw as a big circle. The start state is represented as a node that has an edge or an arrow into it with no source. So this is a transition into the node, but no source node that it comes from, and that indicates the unique start state. An accepting state is drawn as a node with just double circles like this. And finally, a transition is drawn as an edge between two nodes of the graph. So what this says is if I'm in this state that I'm circling in blue, and I read the input A, well, then I can move to this state that at the tail of the arrow. So now let's do a simple example. Let's try to write out the automaton that accepts only the single digit 1. So we'll need a start state, and we'll probably want an accepting state as well. And now the question is, what do we put in between the two? Well, there'll be some kind of a transition here, and it's a good guess that we should take that transition if the machine reads a 1. And now let me take a moment here to talk about how the machines execute. So let's label these states. Let's call this state A, and let's call this state B. Okay. So the machine will have some input, okay, and we can write that input out over here. So let's just say we have the single character 1, and it begins in some state, namely the start state. And so one configuration of the machine is the state it is in and the input. And typically we would indicate where it is in the input by just a pointer saying what position it is in the input. And the important thing to know about input for finite automata is that the input pointer always advances. So or it only advances. So when we read a character of input, the input pointer moves to the right and it never moves back. All right, so from state A, we have a rule. We can see that we're in state A. The next input character is a 1, and that allows us to take a transition to state B. And so now we're in state B, and where's our input pointer? Well, it's beyond the end of the input, indicating we are at the end of the input. And so now this is, we are in an accepting state, and we're past the end of the input, and so we accept. Okay, so let's do another execution. So we start in state A, and let's take as our input the string 0. Okay, and I'd like to draw the pointer, actually, I should have drawn it before the input. So we'll always put the pointer between two input elements. In this case, and it's immediately to the left of the one we're about to read. So in this case, we're about to read 0. So we're in state A, our input is 0. We look at our machine. We see that there is no transition on 0. All right, and so the machine stays stuck. It doesn't make any move at all. And this is our final configuration. And we can see that we're not at the end of the input, and so this is a reject. Okay, so in this case, the machine rejects that string as not being in the language of the machine. Let's do one more example. Let's say that we're in state, well, we're always beginning in state A, in the start state. And let's say our input this time is the string 1, 0. Okay, and our input pointer is there. All right. So again, we're in state A. The input is a 1, and so we'll move to state B. And now the input doesn't change, just the input pointer changes, but I'll just copy the input over to show the difference. So now the input pointer has advanced because we've read one character of input, and now we're in another state. And now we can see that we're in state B. Our next input is 0, and there is no transition on 0 from state B. And so even though we're in an accepting state, B is a final state, is one of the accept states, we haven't consumed the entire input. And so the machine also rejects this string. So this is also a reject. And in general, we could talk about the language of a finite automata that is equal to the set of accepted strings. Okay, so the language of a finite automaton, when I talk about the language of a finite automaton, I mean the set of strings that the automaton accepts. So now let's do a more complex example. Let's try to write out an automaton that accepts any number of 1s followed by a single 0. So once again, we'll need a start state, and we'll also need a final state. And now let's start by thinking about what the shortest string is that's in the language of this machine. So in this case, we know it has to end in a single 0. So a 0 definitely has to be, a 0 transition has to be the last move. And before that 0 can come any number of 1s. And in particular, there could be no 1s. So one transition in this machine is that from the start state, on input 0, we can definitely go to the final state because the string consisting of a single 0 is in the language of this machine. And now the only question is, how do we encode the fact that any number of 1s can precede this 0? Well, there's an easy way to do that. We can just add a self loop on the start state and take that transition if we read a 1. And what does this mean? This means that we'll stay in the start state as long as we're reading 1s, and then as soon as we read a 0, we'll move to the final state, because that has to be the end of the string if the machine is going to accept it. So now let's do a couple of examples to convince ourselves that this works. Let me label these states again. So this is state A, and that's state B. So let's write out here state and input. So we'll begin in state A, and let's take as input 1, 1, 0. Okay, so let's do an accepting case first. All right, so our input pointer begins to the left of the first character. So we're in state A, in start state. We're reading a 1, and that says we should take a transition that puts us back in state A. And so we advance the input pointer. Okay, now we've consumed the first 1. And again, we're in state A, and the next input is a 1, so we'll make another transition to state A. And the input pointer will advance. Okay, so now we're in state A, and the next input is a 0, and so we'll take the transition to B. And now we're in this configuration, so the input pointer has reached the end of the input. We're in an accepting state, and so the machine accepts. 110 is in the language of this machine. So now let's do an example where we will reject the input. And what configuration do we begin in? And again, a configuration for a finite automaton, that just means a point in the execution, and it always consists of a state and a position of the input pointer. So our initial state is A, and now let's just choose the string, I don't know, let's take 1, 0, 0. And let's confirm that this is not in the language of the machine. All right, so we begin in state A, and our input pointer is there. Now we read a 1, and that means so it's from state A on a transition of 1, we stay in state A, and the input pointer advances. And now we see a 0, so from state A on input 0, we make a transition to state B. And now the input pointer is here, so now we're in state B, and we have an input of 0, but there is no transition out of B on 0. There are no transitions out of B at all. And so the machine gets stuck. It can't get to the end of the input. And again, even though we're in an accepting state, we haven't read the entire input yet. And so that means the machine will reject. And so 100 is not in the language of this machine. Up to this point, a finite automaton consumes a character of input every time it makes a move. So if it can make any move at all, the input pointer advances. Now we're going to talk about a new kind of move, the epsilon move. And the idea behind epsilon moves is that the machine can make a state transition without consuming input. So for example, if I have my state, and I'm in state A, and my input, and let's just say that we have x1, x2, x3, and for some reason we're about to read x2. When we make an epsilon move, the machine changes state, but the input pointer stays in exactly the same place. So the new configuration of the machine would be that we're in state B, but our input pointer is still waiting to read x2. So you can think of an epsilon move as a kind of free move for the machine. It can move to a different state without consuming any input. And just to be clear here, the machine does not have to make the epsilon move. It's a choice. So we can decide whether to make the epsilon move or not. Now, epsilon moves are the first time we've mentioned the possibility that a finite automaton might have a choice in what moves it makes. And there's actually an important distinction between automata that have choices and those that don't. So deterministic finite automata have two properties. First of all, they have no epsilon moves, so they must always consume input. And second, they only have one transition per input per state. What do I mean by that? That means that if I look at any state in a deterministic automaton, they can never have something like this, where they have two possible moves for the same input. All the outgoing edges in a deterministic automaton must have different input labels. And then non-deterministic finite automata are just those that are not deterministic. So in particular, a non-deterministic automaton can have epsilon moves, so it can choose to move to another state without consuming input. And they can also have multiple transitions for one input in a given state. So something like this is okay for a non-deterministic automaton. Now let me just point out that really epsilon moves are enough to create non-deterministic automata, and that this second case where you have multiple transitions on the same input can be simulated just by a slightly more complicated machine with epsilon moves. So for example, I can draw this machine in the following way. I can simulate the machine that's circled there in the following way. I can have a state with two epsilon moves, and then each of those states has a move on A. So if I were to label these states 1, 2, and 3, then this would be the state that corresponds to 1, and this would be the state that corresponds to 2, and this would be the state that corresponds to 3. So anytime that we have multiple moves out of a state on a single input, we could always replace that by a few more states with epsilon moves and have every state in the machine only have a single transition for every possible input. So really the only fundamental difference between deterministic automata and non-deterministic automata is whether they have epsilon moves or not. A key property of a deterministic automaton is that it can only take one path through the state graph per input. So this is per input. What do I mean by that? Well, the automaton always begins in the start state, and let's take a very simple input string like ABC. And if we look at the sequence of states that the deterministic automaton will take for that input, this path through the state graph is completely determined by the input because, again, it has no choice. In a given state, there's only going to be one transition labeled A, and it's going to take you to a state that only has one transition labeled B, and that goes to another state that only has one transition labeled C. And so every input determines the path through the state graph that the automaton will take. And this is not true for non-deterministic automata. So it might be, for example, that beginning in the start state and on input A, that there is some state I can go to on that input A, but there may be another transition labeled A that would take me to a different state. So the automaton might be able to go to one of two different states. And again, there might also be epsilon transitions. And so what happens with non-deterministic automata is that in general, as they proceed through the state graph, as they execute on the input, they could wind up in any number of different states. Okay? And the rule with a non-deterministic automaton about when it accepts is that it accepts if any path accepts. So an NFA accepts if some choices lead to an accepting state at the end of the input. That is, the non-deterministic automaton can choose what move to make, and as long as there is some choice it could make that would get it to an accepting state. So let's say, switching colors here, that this was an accepting state down here, and it took this path, then it would accept. And maybe all these other paths are rejecting paths. That doesn't matter. As long as there is one path, one set of choices the NFA could make to get it to an accepting state at the end of the input, then we say that that string is in the language of the NFA. The fact that NFAs can get into multiple different states depending on the choices they make during a run is important and will actually play a central role in a future video. So we're going to do a quick example here to just make sure that this is clear. So here's a little automaton, and note that it is non-deterministic. From the start state, there are two possible moves on input 0. And what we're going to do is just walk through an execution of this machine on a sample input and see what different states it can get into. So we begin in the start state, and we should probably label our states actually so that we can refer to them. Let's call them A, B, and C. And let's say that the first input is 1. And so what does that mean? That means we'll take this transition, we'll just go from the start state and come back to the start state. And so the set of states that the machine could be in after the first transition is just the set A. So it's guaranteed to still be in the start state. So there's no choices with the first move. Now let's say that the second input character is a 0, and now we do have a choice. We could either go to state B or we could go to state A. And we could think of this then as a set of possibilities. that after we execute this move, this transition, the machine could be in any one of a set of states. And actually, this completely characterizes the possibilities for the machine. We've read the second input character, and now we could be in a set of states. Okay, we could be either in state A or in state B. And so now let's say we read another 0. And where could we go then? Well, if we're in state B, we could make the transition to state C. But if we're in state A, then we'll make the transition either to state B or again to state A. So in fact, we could be in any one of the 3 states if we read another 0. Okay? And now I think you can see what the rule is. So at every step, a non-deterministic automaton is in a set of states of the machine. And when it reads another input, we consider all the possible moves it could make to compute the complete set of states it could be in at the next step of the machine. Okay? And then finally, how does we decide whether the machine accepts? Well, we look at the final state after the last bit of input is read, and if there's any, we look at the last set of states after the last input character is read, and if there's any final state in that set, then the machine accepts. And in this case, after we read 0, we see that an accepting state C is in this set of possible states, and what that means is that there was some set of choices that the machine could make that would get it into a final state at the end of the input, and so the machine accepts this input. Okay, so if there's a final state in the final set of possible states, then the non-deterministic machine accepts. It turns out that NFAs and DFAs recognize exactly the same languages, in particular the regular languages. So NFAs, DFAs, and regular expressions all have equivalent power. They can only specify regular languages. DFAs are definitely faster to execute, primarily or entirely because there are no choices to consider. So a DFA can just follow a single path through the state graph, whereas with an NFA, we have to keep track potentially of the set of choices in the NFA, and we might be in a set of states. However, there are some advantages to NFAs. They are in general much smaller than DFAs. In fact, they can be exponentially smaller. So the smallest NFA may be much, much smaller than the smallest equivalent DFA for the same language. And so essentially there's a space-time trade-off between NFAs and DFAs. NFAs might be more compact, but DFAs will be faster to execute. Welcome back. In this video, we're going to talk about converting regular expressions into non-deterministic finite automata. Before we get started, I want to give you an overview of the plan for the next few videos. We have a lexical specification that we want to implement, and the first step is for someone to write that down as a set of regular expressions. Now, that by itself, of course, is not implementation. That's just a specification. So we have to translate that into a program that can actually do lexical analysis. And this actually happens in several steps. The first part is to translate those regular expressions into non-deterministic finite automata that recognize the same, exactly the same thing. And then those non-deterministic automata are translated into deterministic automata. And finally, those deterministic automata are implemented as a set of lookup tables and a little bit of code for traversing those tables. So in previous videos, we've talked about this piece, and we've also defined these pieces. And so now we're ready to put the whole thing together. And in this particular video, we're going to focus on this component right here, the translation of regular expressions to non-deterministic finite automata. So the plan is that for each kind of regular expression, we're going to define an equivalent non-deterministic automaton, an automaton that accepts exactly the same language as the language of the regular expression. And here's a little bit of notation that we're going to use. We'll define these automaton for regular expressions, and usually what we're going to be doing is needing to modify their start states and their final states. So we'll just indicate the start state with the arrow and the final state with a double circle, and we won't worry too much about the overall structure of the machine as long as we have a handle on the start state and the final state. And I should say that in the machines we'll build here, there will only be one final state. Okay, so let's begin. So for the epsilon regular expression, what's a machine that accepts that? Well, this is a very simple machine. We just have a start state and a final state and an epsilon transition between them. So this machine accepts exactly the empty string. Similarly, for a single character A, we can define a one transition, two state machine that accepts that one character. So from the start state, we can move to the final state if and only if we read that particular character. Okay, so those are our two simple regular expressions, and now we have to do the compound regular expressions. And these are a little more involved. So let's talk about concatenation first. And so because we're going to build these machines up from smaller regular expressions to larger ones, we can assume that we've already converted A and B separately into machines. And so I have a machine for A, and I have a machine for B, and now all I have to do is say how I'm going to paste together these two machines to form a machine, a compound machine that recognizes the same language as A concatenated with B. And here's the construction. The start state for the compound machine will be the start state for A, so we just keep that start state for A the same. And then we modify the final state of A. So we make the final state of A no longer a final state, and I've done that here by removing the double circle on the final state of A, and we add an epsilon transition to the start state of B. Now, if you think about it, that does exactly the right thing. What that says is that first we recognize some portion of the input that belongs to the language of A, and when we get to what would have been the final state of A, we can jump to the start state of B without consuming any input, and then try to read the rest of the string as part of the language, as a string in the language of B. And for union, we have a similar way of pasting together the machines, although the structure is somewhat different. So here we add a new start state for the compound machine, and what does A plus B means? It means either the input is in the language of A or it's in the language of B. And epsilon transitions are really good for capturing this because we just make a decision right from the start state, is this string going to be in the language of A or is it going to be in the language of B? So we make a non-deterministic choice, and then we read the string as using the automaton that we chose. And if we get to the final state, either of those machines, we can make an epsilon transition to the new final state for the compound machine. Now remember what the notion is of acceptance for non-deterministic automata. They make these guesses, but if there's any guess that works, then we say that it's in the language of the machine. So if in fact the string is in the union of A or B, then either choosing A or choosing B will work, and so the machine will accept the string. And finally, the most complicated case for iteration A star, we have the following construction. So here's the machine for A embedded in here. We've added a new start state and a new final state. And now let's talk about how this works. So one possibility is, remember that epsilon is always in the language of A star. And so we have this transition here. We can go straight from the start state to the final state and accept the empty string. And so that just guarantees that the empty string is in the language. Otherwise, what do we do? Otherwise, we can make a transition, an epsilon transition to the start state of A, and then we can, from the final state of A, if we reach it, we can go back to the start state of the whole machine. And we can do this as many times as we like. Okay, so there's the iteration of A. It's around this loop right here. Right, and when we reach the final state of A, we could also decide to just make a transition to the final state of the machine. We conclude that that's the last time. And so this machine recognizes 0 or more strings in the language of A. So now let's do an example. So here's a regular expression, and we want to build a equivalent non-deterministic machine that recognizes the same language. And we're going to follow our construction, which works by induction on the structure of the regular expressions, starting with the simple regular expressions and building up to the compound ones. So what do we have here? So we have a machine for accepting 1. Okay, so we need a machine that accepts 1. If you recall, it had 2 states, and it just it made a transition between the two on the number 1. Similarly, a machine for accepting 0. Okay, and now we need to put them together in a machine that accepts either 1 or 0. And the way we did that was we made a choice from a start state for the compound machine. We can either move to the machine for accepting 1 or the machine for accepting 0. And then we have, at the end, also epsilon moves back to the final state of the compound machine. Okay? And now we need to iterate this, so we need to be able to accept 0 or more of 1s or 0s. And so we're going to take this entire block here and paste it into the pattern that we had for iteration. So how do we do that? Well, we have a new start state and a new final state. Okay, and there's an epsilon move from the start state to the new final state to guarantee that we accept the empty string. And then we can just iterate this inner machine as many times as we like. We can make an epsilon move to the start state. We can execute the machine once. And if we decide we want to do it again, well, we can do that. Okay, go back around for another time. Or from the final state, we can decide that we've seen enough and we can just move to the final state of the compound machine. So this machine then accepts the language 1 plus 0 star. And now we have a little bit more to do. We have to accept, we need another machine that accepts just 1. So we build another machine that accepts the digit 1. And now we need to compose the two of these things, to concatenate them. And that was very simple. We just have an epsilon move from the final state of the first machine to the start state of the second machine. And then these are all the states of the final machine. And we just need to now label our final state, the state that we're actually going to use in the end is the final state of the entire machine, which would be that one, and the start state, which is this state over here. And that's the entire construction for the non-deterministic automaton, or a non-deterministic automaton that recognizes this language. Welcome back. In this video, we're going to talk about converting non-deterministic finite automata into deterministic finite automata. Here again is our little diagram of the pipeline of a lexical analyzer, how one is constructed. So beginning with the lexical specification, we write our regular expressions. Last time we talked about this step, the conversion of regular expressions into non-deterministic finite automata. And this time we're going to talk about this step. And as you might guess, in the final video in this series, we'll talk about the final step, which is the implementation of DFAs. So here's the non-deterministic finite automaton we finished up with last time. And the first thing we're going to discuss today is an important idea called the epsilon closure of a state. And the basic idea of the epsilon closure is that I pick a state, and it could be a set of states, but we'll just do it for a single state. And then I look at all the states that I can reach by following only epsilon moves. And so B is the state that we're starting with, so B would be included in the set. And then there's an epsilon move to C, so C would be included in the set, and there's another epsilon move to D, so D would be included in the set. And so we would say the epsilon closure of B is equal to the set B, C, D. And let's do one more as an example. Let's take the epsilon closure of G. And when we switch colors, I'll do this one, I'll erase that and do this one in pink, or purplish pink. So the epsilon closure of G, well, we just have to follow all the epsilon transitions out of G. So H would be in the epsilon closure of G. But it's not just single epsilon moves. This is recursive. So any number of epsilon moves that I can take, all of those states are included in the epsilon closure of G. So in fact, I would also be included, A would be included, and B and C and D would also be included. And now, if I look at all of these states that have been colored in the light purple color, I can see that I can't reach any new states from those states using only epsilon moves. And so the epsilon closure of G would be equal to, and now let's write them all out here, it's A, B, C, D, G, H, I. Okay, so that is the epsilon closure of a state. Recall from the last video that an NFA may be in many states at any given point in time. That is, because of the choices it can make for a given input, an NFA may reach multiple different states. And the question we want to address now is how many different states can it be in? Well, if a non-deterministic automaton has n states and it winds up in some subset of those states S, how big can that subset be? Well, clearly the cardinality of that set has to be less than or equal to n. So the NFA can get into at most n different states. Now, if instead I want to know the number of different subsets, well, how many different subsets are there of n things? Well, that means there are 2 to the n minus 1 possible subsets of n states. And there's something very interesting about this number. First of all, it's a very big number, so clearly the NFA can get into lots of different configurations, particularly one that has a lot of different states. But the important thing is that this is a finite set of possible configurations. And this is going to give us the seed of the idea for converting an NFA into a DFA, or a deterministic automaton. Because all we have to be able to do to convert a non-deterministic automaton into a deterministic automaton is come up with a way for the deterministic automaton to simulate the behavior of the non-deterministic automaton. And the fact that the non-deterministic automaton can only get into a finite set of configurations, even if that set of configurations is very large, is exactly what we will exploit in the construction. Now we're ready to give the construction showing how to map an arbitrary non-deterministic finite automaton to an equivalent deterministic finite automaton. So let's begin by saying what's in our NFA. So we'll have a set of states, which we'll call S, and these are the states of the non-deterministic machine. There's a start state, little s, which is one of the states, and there's a set of final states, capital F. And then we also have to give the transition function, and I want to write out the state transition function. I want to use the state transition function to define a operator that we're going to find handy for defining our DFA. So let's say that A applied to a set of states. So X here is a set of states, and A is a character in the input language. So A of X is equal to those states Y, such that there is some X, little x here, a single state, in the set of states, such that there's a transition from X to Y on input A. Okay? So this is just a way of saying, of giving the transition function at the set level. It says, for a given set of states X, show me all the states that you can reach on input A. All right? And then the other operation that we need is the epsilon closure operation that we defined a couple of slides ago. And I'm just going to abbreviate that as epsilon dash CLOS, epsilon close. All right, so now we're ready to define our DFA. So what will the DFA be? Well, it's going to have all of these things. It's going to have a set. We're going to have to say what the states are, what the start state is, what the final states are, and what the transition function is. So let's begin with the set of states. The states will be the subsets of S. So the states of the DFA will be all possible subsets of the states of the NFA. So there'll be one state of the DFA for each possible subset of states of the NFA. And of course, this is potentially a very big number, but it's still finite. And so we can use that set of subsets of states as the state space of the deterministic machine. So now, what's the start state of the DFA? Well, that's going to be the epsilon closure of the start state of the non-deterministic machine. And if you think about it for a minute, this makes sense. What we want to do is we want to keep track of what set of states the non-deterministic machine can be in. And each state of the DFA corresponds to a different subset of states. So each individual state of the DFA tells us a particular set of states the NFA might be in. Well, which set of states might we be in at the beginning? Well, clearly the NFA starts in its own start state, but then before it reads any input, it can make epsilon moves. And so the actual set of states it could be in before it reads the first input symbol is exactly the epsilon closure of its start state. Now, what are the set of final states? Well, the set of final states will consist of those states X, and remember the states of the DFA are sets of states of the NFA, so that X is a set, and it's going to be every X such that X intersected with the set of final states of the NFA is not empty. So any state of the DFA that has at least one state of the NFA, one final state, excuse me, of the NFA in it is good enough as a final state for the DFA, because remember, the goal of the NFA is just that it has some computation which accepts the input. It means there's some way to get to a final state. And so if any of the states is a final state, we're happy. And we can capture that here by just considering every state that has at least one final state of the non-deterministic machine as a final state of the DFA. And finally, we need to define the transition function. And how do we do that? Well, we need to say that for a given state X and another state Y, when is there a transition between them on some input A? Well, that there will be such a transition under what conditions? And, well, let's write them out. So remember, we're in state X. And what do we need to know? Well, we need to know the set of states that we can reach on input A. And we just defined that. That's A of X. And then once we've gotten to one of these states, once we've seen where we can go from the set of states X on input A, there's also the possibility of making epsilon moves after that. So furthermore, we have to take the epsilon closure of that set of states. Okay? And so we'll say that there is a transition from X to Y if Y is equal to this set of states. All right? And notice that there's only one such set of states for any X, and that guarantees that this is a deterministic machine. Each state will only have one possible move on each input. So we can just now go through our checklist and see if we have a deterministic machine. We have a finite set of states, we have a start state, we have a set of final states, and we have a transition function with only one move per input and no epsilon moves. And so that is, in fact, a deterministic machine. And the property that it maintains is that each step of the computation, the state of the DFA records the set of possible states that the NFA could have gotten into on the same input. So let's work through an example of constructing a deterministic machine from a non-deterministic machine. Here's the non-deterministic finite automaton that we built in the last video, and again, this is the one I used at the beginning of the video to define epsilon closure. So we're going to do the example slightly differently than the construction I gave on the previous slide. If we actually had to write out all the subsets of this many states, it would take us a very, very long time. And it turns out that not all of the subsets are actually used by the DFA. So we're just going to enumerate the states that we actually need, and we'll do that by beginning with the start state of the DFA and then working out which additional states are required. So how do we do that? Well, we begin with the start state of the NFA, which is just this state A. And then recall the start state of the DFA is the epsilon closure of that state. So that corresponds to this purple set here. All right? So the first state of the DFA, the start state, is the subset of states A, B, C, D, H, I. And now we have to work out from this particular state, from the start state, what happens on each of the possible input values. So the alphabet of this machine is 1 and 0, so we have to have two transitions out of this state, one for an input of 1 and one for an input of 0. So let's do input 0 first. And we can see, looking at the purple set, that there's only one possible transition, and that's from the state D to the state F. Right? So certainly the state F is included in the set of states that the NFA can reach. But then once we get to state F, there's a lot of epsilon moves that we could take. And so in fact, the second state of the DFA corresponds to a much larger set. It's the epsilon closure of F. And that is this set of states, F, G, H, I, A, B, C, and D. Okay, so this is the set of possible states that the NFA could be in after reading a single zero. Next, let's consider what happens from the start state on an input of 1. Which possible states can the NFA reach? And if we look at the transition function, we see there are two possible moves that the NFA could take. It could be in state C, in which case it would move to state E, or it could have been in state I, that's also part of the purple set, in which case it would move to state J. So there are two possible states that the NFA can get into as a result of reading a 1. And then after that, there's a bunch of epsilon moves that can take place. And in fact, it turns out that after reading a 1, the machine could be in any state except for state F. And that's this set of states. And you'll notice that this particular set of states, the red set, includes the final state of the NFA. So this is also a final state, indicating that after reading a 1, the NFA could be in an accepting state. And so this will be an accepting state of the DFA. Well, we still have to fill in for both of the two states that we've added here, the two states on the right of the machine, what they do on input 0 and what they do on input 1. So let's figure that out. So beginning with the red state, on input 0, what can happen? Well, look, the red state includes state D, and it can move to state F, but we've already computed what happens on the epsilon, what the epsilon closure of F is. That's just the green state. And so if I'm in the red state and I read a 0, I move to the green state. If I'm in the red state and I read a 1, you'll see that both states, NFA states C and I, are in the red set, and so it just takes us back to the red set. And similarly for the green state, if I read a 1, I move to the red state, and if I read a 0, I stay in the green state. And so this then is our deterministic machine. Down here, this is the deterministic machine, and again, it simulates the NFA. So on every move of the deterministic machine, it records the set of possible states that the NFA could be in, and it will accept a string if and only if the NFA could accept the string. Welcome back. In this video, we're going to wrap up our presentations on lexical analysis with a discussion of how we implement finite automata using a variety of different techniques. Just to review, here's our little flowchart of how lexical analyzers are constructed. And today we're going to be focusing on this last step, the implementation of DFAs. And actually, I should say that this chart is not quite completely accurate because sometimes we don't go all the way to DFAs. We stop with NFAs and we implement them directly. And so we'll also talk a little bit about that. What if we didn't want to build a DFA and instead wanted to base our lexical analyzers directly on an NFA? So beginning now with DFAs, it's very simple to implement a deterministic finite automaton as an array. This two-dimensional array, and one of the dimensions will be the state. So we might have states here, and the other dimension will be the input symbols. And so I might have a state I and an input A, and I simply look up in that position, and there will be the next state, K, to which we're going to move. So the table stores at every particular input symbol and state the next state that the machine will move to. So let's do an example of converting a deterministic automaton into a table-driven implementation. So here is the automaton that we built last time, and recall that several videos ago we started with a regular expression which we converted to a non-deterministic finite automaton, and then we converted it to a deterministic automaton just in the last video. And here it is again. And now let's talk about how to realize it as a table. So we draw a two-dimensional table, and there are three states, so we'll need three rows. And I'll just label these rows S, T, and U. And then there are two inputs, 0 and 1. And now let's fill in the entries in the table. So in state S, on input 0, where do we go? We go to state T. So the entry in the S0 entry will be T. And similarly, from state S on input 1, will wind up in state U. So the S1 entry will be U. Okay, and then similarly for the other rows of the table, let's do the T row next. On 1 we go to U, and on 0 we stay in T. So this row is also TU. And finally for U, what happens? Well, on 0 we go to T. And on 1, we stay in U. So this row is also TU. And there's our table. That describes the transition relation of the automaton. And now if we were to think about how we would use this transition relation in a program, you can easily imagine. We would start out, say, with our input index pointing to the beginning of the input, and let's call that 0. And we'd have to have a current state, and we start in the start state, and let's just say that that's row 0, so in this case that would be row S. And then while, what do we want to do? We want to walk over the input and check whether and check on the, and make the transitions for each element of the input one at a time. And we want to stop when the input is empty. So while there still is input, let's say we have an array of characters that is our input, and while the entry in that array is not null, let's do the following. We're going to update the state at each step, and what are we going to update it to? Let's give this array a name. Let's call this array A. So we're going to look up in our transition relation A, and what are we going to use? Well, we're going to look up the current state, and we're going to look up the input. And in that entry, using the current state and the current input, we're going to transition to a new state. And we also want to increment the input pointer. So we'll do that at the same time. And there is our loop that processes an input according to the transition table A. And as you can see, this is a very compact, very efficient process. Just a little bit of index arithmetic and two table lookups, one for the input and one for the state transition table per character of input. So it's really hard to imagine having a process that's much faster or more compact than this. Now, that was one strategy for implementing a deterministic finite automaton. And you may have noticed that one disadvantage of that particular approach was that there were a lot of duplicate rows in the table. In fact, all the rows of the table were exactly the same. And we could save some space by using a slightly different representation. So instead of having a two-dimensional table, we could just have a one-dimensional table. And this table, again, would be one entry for each state, so S, T, and U. And what this table would contain is a pointer to a vector of moves for that particular state. So there'd be a pointer here, and it would point to another table, another one-dimensional table, that would say what we should do on 0 and what we should do on 1. So in the case of S, we wanted to move to state T if it was a 0 and to state U if it was a 1. And now, when we go to fill in the entry for t, we see we don't need to duplicate this row. We can actually just share this row, and similarly for u. And so this table, this representation, is actually much more compact. We just share the rows that are duplicated in the automaton. And it turns out that in the kinds of automata that we look at for lexical analysis, it's very, very common to have duplicated rows. And so this can actually result in significant compaction of the table, particularly when you consider the number of possible states. Remember, there could be 2 to the n minus 1 states in a DFA for an NFA with n states. And while the blowup is often not the worst case, it can be very substantial. And so the two-dimensional table we had in the previous slide could actually be quite large, and we can sometimes have a much more compact representation by little tricks like this. Now, the disadvantage of this particular representation is this extra indirection right here. I mean, these pointers actually take time to dereference, and so now our inner loop will be a little bit slower. We have to do a table lookup, dereference a pointer, do another table lookup, and then we can make the move. Finally, it's also possible that we might not want to convert to a DFA at all. It might be that the particular specification we gave is very expensive to turn into a DFA, that the tables just become truly huge, and we might be better off just using the NFA directly. And so one can imagine an implementation of an NFA as well. We could also implement that via a table. In this case, we would have to have a row for each state in the NFA. And we won't do them all here. But we could have rows for every state of the NFA, and then where we're going to go if the input is 0 or if the input is 1. And so in this case, and I almost forgot, we would also need a transition in the most naive or the most straightforward implementation of an NFA where we would go if on epsilon. And now, remember, because these are NFAs, in general, this will be a set of states because we might have more than one epsilon transition or more than one transition on 0 and 1. And so in this case, on epsilon, A can go to B. So this would be the set of states B. And B can go to C or D. And C can only go to E on 1. All right, and D can go to F on an input of 0, and so on. We fill in the rest of the table. And this table is guaranteed to be relatively small because the number of states is limited by the number of states in the NFA and the size of the input alphabet. And once again, we could do sharing of common rows and other tricks like that to compress the table if we like. But now the inner loop for simulating this automaton is going to be much more expensive because we have to deal with sets of states rather than single states. So at every point in time, we're going to be tracking a set of states, and when we go to do a move, we have to look up for every state in the set where it can potentially go, including things like the epsilon moves and carrying out all possible epsilon moves, so we always have an accurate assessment of the complete set of states that the NFA could reach. So while this saves a lot of space in terms of the tables, in terms of the size of the tables, it can be much slower to execute than a deterministic automaton. To summarize, a key idea in the implementation of lexical specifications is the conversion of non-deterministic finite automata to deterministic finite automata. This is what takes a general high-level specification using regular expressions and converts it down to something that's completely deterministic and only uses a few operations per input character. Now, in practice, tools provide trade-offs between speed and space. So DFAs are faster and less compact, so the tables can be very large, and at times that's a practical problem. And NFAs are slower to implement, but more concise. And the tools give you generally a series of options, often in the form of configuration files or command line switches that allow you to choose whether you want to be closer to a full DFA, something that's faster and perhaps bigger, or to a pure NFA, something that's slower but consumes less space.